Okay, so looking at entropy of a system. So entropy is a new term for you at this point in time. So it's essentially a way of describing a change in disorder. Okay, so entropy is essentially a measurement of energy distribution in a system. So like enthalpy, okay, we can only really truly measure the difference in entropy within a system. So meaning comparing what was the entropy at the beginning versus at the end. One way to think about entropy, so it's essentially a disorder. So it's a measurement of disorder of a system. So which sounds weird to do, but basically how this works is that you have you're looking at essentially the movement of the particles. In a nutshell, the more freedom of movement the particles have, or you think of it as the greater the random movement of the particles, the greater the entropy of a system. So for example, let's say we are going from, we're comparing a sublimation reaction. So let's say we have solid carbon dioxide, sorry, I'm writing with a mouse today, solid carbon dioxide going to gaseous carbon dioxide. Okay, so we have a phase change here. The particles of the gas have much more movement associated with it compared to the particles that are in the solid. So because there is an increase in movement, there is an increase in the entropy, or in this case, there's an increase in the entropy of the system, or you can say it has a positive delta S. There is more disorder or more movement in the products than there are compared to the reactants. Now, this can be compared using different things. Actually, before I get into that, you can have this in comparison to a chemical reaction. This is an example of a phase change. What you have to think about is what is the difference between the particle movement before and after. Okay, so I'll give you an example. I'll write on the board for this one. So let's say here we have a dissociation equation. So this is where we have our solid ionic compound, and it's essentially being dissolved in water into the free form ions. So again, this is an example where you have ions that are dissolved in water, right, that have much more movement in comparison to the solid crystal lattice structure. So you're comparing the amount of movement. Now, if I have a chemical reaction, let's say, that involves various things. Let's say we have, sure. Okay, so let's say we have the formation of water. So here we have actually less movement on the product side. The reactants have much greater movement because we have gaseous reactants and we have a liquid product. So in this case, this is actually representing a decrease in randomness or a decrease in entropy. There is less movement at the end in comparison to where it began. And remember, it's always products minus reactants anytime we're doing a change in. So when you're looking at this, you have to kind of consider the particles. Now, what if we had gases on both sides? What you would then do is compare the amount of moles for those gases. So let's say we have here, give me a second. Okay, so let's take a look at a combustion reaction just for example. So we have here C6, oops. C6H12O6 solid plus O2 gas, making carbon dioxide gas, and water gas. Okay, so for balancing here, we would need a 6, and then we would need another 6, and then actually that ends up being another 6. Okay, so here we have a case where we have, so our reactant has a solid. Okay, so we know solids have less movement in comparison to, in this case, gases or liquids. So we have solid on the reactant side, but we have gas on both sides. If you have a case where you have gaseous products and reactants, what you would do is you would essentially compare the amount of moles of it, or look at the coefficients. So on the left side, we have 6 moles worth of gas particles, and on the product side, we have 12 moles worth of gas particles. So in a nutshell, so first of all, just by looking at this, we can see there's no solid on the product side, but there's way more gas particles. So there is actually an increase in entropy here once again, because we have more movement on the product side in comparison to the reactant side. So in this case, again, we have a positive change in entropy. Okay, now when you're looking at entropy changes, what does this have to do with anything of what we're talking about? Okay, so there's a concept known as Gibbs free energy. So Gibbs free energy really discusses what is the possible amount of energy available to do work for us. So for example, it's not energy that is used to, create bonds or to break bonds. We're talking about excess energy. So energy that we can use to perhaps, spin a turbine, or to heat up water, or to light a light bulb. Just looking at different ways that we can use energy. So essentially it's talking about, is there free energy available? And then of course we can use that information to figure out, well, what can we now do with it? So delta G is essentially the symbol for change in Gibbs energy. And how we calculate that for a system is we look at the change in enthalpy and we subtract the change in entropy, taking into consideration a multiplication factor for temperature, of course, in Kelvin. Okay, so you will not be expected to do these calculations, but I do want you to understand what it means to have, let's say, a spontaneous versus non-spontaneous reaction. So a spontaneous reaction would indicate that we have available free energy. So how that happens is we need a couple of things to go down. So first of all, this has to be an exothermic process. So meaning there has to be energy that is released overall. And we have to have an increase in the random or movement energy of the particles. So by having excess energy released in enthalpy and more movement, that's typically an indication that we are going to have a spontaneous reaction. So spontaneous reactions always result in a negative delta G value. So what happens if something is non-spontaneous, so we don't have available free energy? Well, typically that means we have an endothermic process and there is less available movement of particles in comparison to what they were as reactants. So a positive delta G, it would actually indicate that the reaction is not spontaneous. So meaning if we wanted a reaction to actually happen, if we have a non-spontaneous situation, energy has to be put in. And that kind of makes sense because it would be an endothermic reaction anyways. So energy would have to go in to have the products be made instead of having them spontaneously happen. So obviously, if you want to have extra energy to do some work for us, you would have to have the scenario that would give us a negative delta G value. Okay, so exothermic and entropy increase. So you should be able to look at a scenario and discuss if entropy is increasing or decreasing. And of course, you do know already if something is exothermic or endothermic, or if you have information to calculate that. So you should be able to basically say if a spontaneous reaction would be able to occur. Now, like I said, you're not going to be doing any number crunching here, but you should understand the criteria and the relationship between these values.